Okay, so good afternoon, everybody. I hope you had a great lunch break, but we have to start. So there will be a little change in the program, and I wish to greet Professor Caio Bragado, now from Alfred University, who will give his talk on models for ionic conductivity in glasses. Please.
Great job, Thomas. Hi, everyone. You guys can do it. Let's keep awake, stay with me. I'll try to be as dynamic as possible. We'll be walking around, pacing, so pay attention, out of your phones, eyes on me. Great. So my name is Caio Bragato. I'm from Alfred University. But the first thing that I want to say is that in 2015, I was sitting in your chair. I was a student here at the summer school, and it was one of the greatest experiences that I had as a PhD student. While I was sitting there, I sent a couple of messages to some old friends of mine and got a response from all of them. So I hope that you guys had a good time and had time to mingle. This is something you're going to remember for a really long time, believe me. But okay. My work today, or my presentation today, sorry, is going to be on models for ionic conductivity. So it's going to be a little bit different from our previous session, but we're going to start in the same spot. We're going to start talking about diffusion. So when we're talking about these models for ionic conductivity, deep down there's still transport of mass, so mass transport through this amorphous medium. Our understanding of this mass transport is given by Fick's laws. I'm going to simplify things. I'm going to stay mostly around Fick's first law, but we can talk. Sorry, we can talk a little bit more if you guys want to hear about the second part. But the idea here is to define this parameter here, D, which has already been introduced in a couple of talks, including Professor Thomas' talk earlier today. But this is known as the diffusion coefficient. So let's keep that in mind, and this is going to be one of the most important things to understand when talking about these ionic conductivity models. This law, as I said, you can also go for the second of Fick's laws, which is just a derivative. And I think this one is a little bit better to understand because we're looking at this change of the concentration with a profile, right? So if you guys had your material science courses and you study the diffusion of carbon and steel to harden some of the gears, maybe you saw some of the Fick's laws. And sometimes we think about this deep profile. But maybe you can see the relationship that we have here with electrical properties as well, because we're thinking about this movement of this matter, this charge carrier for our case, within the material. And just to give a historical context as well, this is our friend Adolf Fick, who came up with this theory, and originally was a discussion around biological systems. We just adapt a little bit, as we do a lot. And of course, from that, we can extend a little bit our understanding, and also with the concept, hello, my friends and colleagues from Alfred. I'm glad you guys are here to support me. Good cookie, great. So back to what I was talking about. The diffusion coefficient, we can try to understand that a little bit better through the Brownian motion. So if you're not familiar with it, originally was also mostly around biological systems and dispersion of matter. But we then start applying for a lot of different things involving the movement of particles. And Einstein, I think, was one of the ones who brought this equation or this concept to a next level using this relationship here in which the diffusion, oh, this pointer is tricky. I heard the whole week that the pointer was tricky. I was not expecting that. Okay, so let's see. So if I start like here, oh, that's better. All right. So we have this terminal drift velocity of the particle when we have an applied force here. And this ratio of the velocity drift divided by force is something that we name as the mobility of the diffusing species. The driving force not always is super clear, but for us, thinking about ionic conductivity and the movement of this charge carrier, you can clearly see that this driving force is going to be the external electric field, all right, when we are doing the measurement. Or if you're thinking about a battery, it's going to be the chemical potential between the two sides of the battery that are going to create this driving force that's going to push this particle on a certain direction. As I said, it is clear for us that this electro force, this external electric field, is going to be what is going to be pushing our charge carriers. But it was made more clear into an equation by Nernst. On his interpretation, he just renamed that mobility into the mobility in the case of an electric field, and therefore creating a dependency with the charge of this particle that's moving. Of course, this movement of the particle is going to be dependent on the charge it carries. Again, trying to bring back from your physics courses, if you ever had to calculate the speed of an electron under an external electric field, if you had to calculate a cathode tube, that's more or less what I'm thinking of, right? So I'm trying to see what's the force of that electric field in the charge. And this is how, I can do it. There you go. This is how we understand mobility for the ionic conductivity. As it has been presented today as well, earlier, the electrical conductivity, independently if we're talking about electrons or ions, is going to be equal to that equation here, or at least is the easiest way to interpret it, where Z times E is going to be the charge of that charge carrier, right? It's going to be the valence times the fundamental charge of an electron. And then I have N, which is the effective number of charge carriers. And mu, that's the mobility that we just defined using the diffusion. And if I replace that mobility by the relationship that Nernst proposed, the conductivity then looks something like this, which then is known as the Nernst-Einstein equation. Sorry, let me go back just a second. So these two equations are going to be fundamental throughout my discussion. I want you to memorize them right now. Everyone memorized? Just kidding. I'm just going to be bringing the case. You don't have to memorize. But what is important for me is that you remember that in this equation, considering a single type of charge carrier, I'm not changing the type of charge carrier. Z is going to be constant. E is constant. Boltzmann's constant, surprise, it's a constant. And then I'm going to have the other terms possibly varying. Now, since we're talking about ionic conductivity, and we already saw some electronic conductivity, I think it would be interesting for us to understand how it changes for different glass systems. So I'm going to change a couple of things individually, and we're going to discuss a little bit how those things are going to affect the change in ionic conductivity itself. I think the first one that is obvious for us to think about is the temperature dependency of ionic conductivity. If you think about raising the temperature, you're going to affect the diffusion. You're going to increase the speed, the mobility, jump frequency, doesn't matter. We still have to discuss that when we discuss the the models. But for us, I think you can see that putting more temperature is going to make these things move faster or more. More of them are going to move. Through experimental results, and also, again, as Professor Thomas discussed earlier today, the diffusion, since it is an activated process, we also know that experimentally, the conductivity is also an activated process, meaning that it has a linear dependency with temperature, and that slope of this linear dependency is proportional to the activation energy. Steeper the slope, higher the activation energy. There's another thing that I want to point here on this extremely clear and very visible graph that you can read everything that's written on it. That it's a comparison between crystal conductors and amorphous conductors. The crystal ones, the crystal ones are the dashed, and the amorphous are the lines. You cannot read the compositions, are many different compositions, but this graph you can find in Varshnaya and Morrow's book. I'm pretty sure you guys have it, or if you don't, let us know, because you should. But in general, the glass material has a higher conductivity than its crystalline counterpart, meaning that the amorphous material in general is more conductive than the crystal. Is this always true? No. There's always some exceptions, but in general, that is the rule. In general, that's the rule. Great phrase, Kyle. All right. Now, composition dependency. From the equation that I just showed you guys, I guess that you would think, you know, if I put more alkali, that is going to be my charge carrier, the glass is going to be more conductive, right? What is the equation dependency again? ZE, that's constant, and mu, right? So if I increase N, I should increase ionic conductivity. Is this always the case, Vinicius? That was the answer. No, it is not always the case. There are a couple of different exceptions that I can show you guys. I would say that the most famous one is the mixed alkali effect, shown here on the right graph, in which I have an increase, or sorry, I have a constant value of alkalis, and if it was only dependent of N, that should be a straight line. But as you can see, it is not. This is because I'm mixing sodium with lithium. Historically speaking, this is also known as the thermometer effect. If you want to know more about why, just go do a Google search. I don't have time for this. But I would say that normally you would expect something like this, right? You increase the alkali concentration, and you increase the ionic conductivity itself. Another interesting case is with borate glasses. Again, being the last one, or one of the last ones, the last session, let's say, has its advantages because I can just quote the previous speakers, and if you don't remember, that's your fault, not mine. But we already discussed about the idea of the boron anomaly, and you can see that for borates, especially here on the first graph, I have a decrease in activation energy with an increase of N4. So here I have a linear behavior of the activation energy, and this is also true. I should have chose the conductivity graph, but this is also true for conductivity. Conductivity increases as you increase the alkali concentration, but you can see that eventually there's a change on the mechanism, behavior, whatever is happening, there is a change. We normally would associate that, of course, with the boron anomaly. Maybe I'm affecting the mobility of the ions because I'm changing the glass structure in a different way. Maybe I'm changing the number of active charge carriers. Maybe not all ions there are going to be as mobile as they used to be. But what is important for us is that this thing is not linear with composition. So it's not as straightforward as one would expect. There are two interpretations in the literature. I'm going to discuss this a little bit further. with you all, but I would say we can put this in one of two boxes. Conductivity, again, proportional to mobility times number of charge carriers. So you can think, am I changing mobility or am I changing number of charge carriers? From chemistry, those two approaches are either known as strong electrolytes or weak electrolytes. Strong electrolytes, meaning that all ions are dissolved within the glass and all of them would be available to move. The weak electrolyte is you have a dissociation equilibrium or you have a pre-stage. We're going to discuss this in some of the different models again. And that would make the number of effective charge carriers what dictates the ionic conductivity. Great. We also have, I feel obliged to say this one as well. There is also a thermal history dependency of ionic conductivity, definitely not as strong as the compositional dependency. The compositional dependency, I should have pointed out, you change by orders of magnitude by changing the composition. Even though you just change from 10 to 20%, you can increase by 1 order of magnitude even. But nonetheless, there is a thermal history dependency. Here's a very nice study that we did here at Lamave during my PhD. Danielle, Anna, Jean-Louis, and I. This idea I had back in 2015, but Anna had it before. But what is nice is that we were able to do that in situ. So here is not a fitting, is just the data. So that line is not a line, it's a bunch of individual points. That was a lot of data processing. Thanks, Danielle. And this work has been continued. Ricardo saw me preparing this presentation and made me add a figure of his work as well. He has actually some very interesting results. I would recommend going to his poster or talking with him as he develops this work. So far, I don't know, Ricardo, maybe you can correct me, but so far we studied just a few systems with this structural relaxation. I did on silver metaphosphates. Ricardo did on some silicates, right? And the phosphate as well. This one is phosphate, right? Lithium phosphate, yeah, perfect. So anyway, we know there is a thermal history dependency there. And again, we can try interpreting this, right? Conductivity depends on what again? Mobility and number of active charge carriers. What are we changing by changing the thermal history in this case? Are we changing the free volume of the glass and therefore affecting the mobility? Are we affecting the free energy of the system and therefore increasing or decreasing the energy to form a charge carrier? Let's try exploring that. So the models for ionic conductivity, if you think, again, we took the Brownian motion from biology, we took Fick's law from biology, so let's look closer to our home and take something from them. Looking at ceramics and crystals, when you think about diffusion, the idea is that diffusion of ionic species, of atoms, is going to happen through defects, right? So you're going to have defects jumping around. Normally, when you think about a charge carrier, either if it's part of the structure, you're going to need a hole, and then you can think about even the hole movement instead of the charge carrier movement. And we can try bringing that idea for the glass, right? So we have to define what is a defect, what is the charge carrier. If it's the same thing as in the crystal, would it be a hole or not? But I'm here, I'm going to present you guys a couple of the models that we can find in the literature. It's not all models in the literature. I have a limited time. But are some of the models that I think represent a lot of interesting aspects that you can think of. All right, let's start historically with the first more well-accepted. If you haven't done a lot of ionic conductivity and you're looking for something to understand ionic conductivity, is a great place to start, which is the Anderson-Stewart model back in the 50s. So the Anderson-Stewart model was trying to understand that activation energy. So what dictates that change of ionic conductivity with temperature. What affects that? And in this model, the authors divided that energy in two different contributions. The first one is the energy necessary for breaking the bond in which the alkali is. So if I get an alkali and I put in a glass, where is it going to be? Next to what? A non-bridging oxygen. Yes, a non-bridging oxygen, right? So if you're thinking about an oxide, it's going to be the alkali here next to a non-bridging oxygen. And the first energy that I need to make this thing move is to kick it out of its comfort zone, right? So I'm just going to kick that alkali out, and then once it moves, it has to distort the network around it. We're not talking about electrons. Electrons are tiny. They can tunnel. They can go far without creating a lot of distortion. Ions are chunky guys. They have to move around. They're going to push things around. So there's going to be an energy associated also with the distortion of the network. So we call those energies binding and distortion. In this case, I'm just going to point out that I show in this graph here this little shoulder, but there's no intermediary stage, right? There's no metastable, there's no, it just goes. Both of the things are intertwined and connected, okay? It has this shoulder just to show that you have those two. All right, so once you do that, with that, we can try to rewrite the equation for the ionic conductivity as a function of temperature. We're looking at the temperature dependency equation. The authors have rewritten that binding energy with this equation here. I'm not going to bother on going too deep. I recommend you guys reading the article if needed. And also the strain energy. In this case, I'm going to point out that is proportional to the shear modulus here. I'm pointing this out on purpose because on the work, the authors propose that what controls the ionic conductivity is actually the shear modulus. Of course, there are different ways of testing it out. I'm glad Marcel just got here. Marcel has a very nice series of works in which he tested this for different glasses and models. And we are trying to extend that search. And this is a recent work of mine that it hasn't been published yet, but it, you know, maybe the reviewers are busy with something. It has been like waiting for a month and a half. In which we look at the packing fraction or the free volume using two different techniques, and we try to explain the behavior of the borates. Anyone has any idea why I'm looking at the packing fraction? Yeah, to have an idea about the free volume, but I'm testing Anderson-Stewart model. Why would I be looking at the free volume? To study strain energy. The free volume is going to be proportional to the strain energy. Therefore, the free volume should be proportional to the ionic conductivity. And you can see there is some relationship. There's some linearity, but it breaks down eventually. All right, so with this, we can go to our next one and start thinking a little bit deeper on the models. The second one that I want to show you guys is Charles' model, in which the author proposed some different events that might happen in your glass. So the event one is just a polarization by rotation. That's not super interesting for us. Things are just spinning around. But the other ones are very interesting for us. So the first one that I want to point out is this defect formation. So once again, we can think about this 2 as a non-bridging oxygen. and then you have the alkali jumping to the second part here. And that's what the author, Charles, called a defect formation. And then you can have some other, you can have a defect migration without polarization, with polarization, or defect annihilation with polarization. That would mean the things going back to place. So this is interesting because in the previous model, I ignored completely the number of charge carriers. I didn't think about anything. I just said they're all equal to each other. In this case, I'm actually making a differentiation here, right? So I actually have, oh, let me try it again. Where are you? Okay, cool. So you have the defect formation that would be creating the charge carrier. So it's not every alkali that can move, it's every alkali which is in this situation here. So I actually create a separation between forming the charge carrier and moving the charge carrier. And I would say that's the main difference on this model. Again, in their work, the author separates here, so you can see the formation is divided by 2, plus the migration energy. Which is really interesting for us, because now we can start thinking it's not every alkali that can be moving, right? I'm separating those, so I don't have necessarily every alkali moving. Of course, I have to talk about Ravane and Souquet, if you're not familiar with it. Souquet was my co-advisor, and I did a lot of the work on this. He spent a lot of time here in Lamav. Great guy. So back in the 77, Souquet was thinking about this problem of the migration and formation of charge carriers. And he, as a chemist, related that to some chemical background. So again, borrowing from nearby sciences, he proposed that glasses can be considered a solvent with the alkali salt as a solute. So the same way that you can dissolve sodium chloride in water, you are dissolving sodium oxide in silica. But different than dissolving salt in water, the oxide sodium is going to be weakly dissociated. So instead of everything going to its ionic form, it's just going to be partially on that ionic form. It can be shown here by this equation. So here, this is tricky. All right, so here I'm adding half of this alkali. It can be sodium, lithium, whatever, from your first row, and a silica. And when I do, I have this reaction, but dissociated. Not dissociated, I guess would be better, but I have the situation in which I have the oxide with the alkali here. And you can see that this reaction happens, right? When you put everything in the crucible and you melt, it's going to go into that direction. You're not going to have, unless if you put too much, but you're not going to have a phase separation. They're going to be there. And once you're here, you're going to have this dissociation equilibrium. So you're going to be jumping back and forth. And you have this metal or this alkali metal here with this non-bridging oxygen, or it's going to be far enough, thermodynamically speaking, that it's going to be considered dissociated. Taking that rationale, we have this proposal in which the number of charge carriers is going to be proportional to the dissociation constant times the square root of the activity, chemical activity of silver iodide. Anyone knows what chemical activity is? Anyone awake? After lunch crew, hard. Lauren? It's going to be the effective concentration. So I'm talking about the concentration of the dissociated ion here. And you can see that, again, in the work that we published here in Lamav, there is a linear dependency between the activity and the ionic conductivity. Very interesting results. We start showing this relationship and maybe this idea of not every alkali can move is giving us some good results. All right, then we can have a little bit of a thought, maybe a little bit more on just thinking on the energy levels and thinking maybe about not necessarily the same way as Colin did, but thinking about energy landscapes. So you can think about every ion being on a little pocket of energy. They're comfortable, they want to be where they are. And very similar to the Anderson-Stewart model, you just kick it out, right? You just have a kick of energy, punch it out of its place. If this was a crystal, this would be a very regular and homogeneous spots, right? Because you have regularity on the structure, all the energy spots are going to be very similar. But because we're talking about an amorphous system, you're going to have a little bit of a variation on the energy. And in this model, what is interesting for me is that it brings the time constraint. We saw from Professor Andrea's presentation that when you're thinking about polarizity, when you're thinking about the dielectric, you also have to think about how much time you're giving your system to respond. You're going to have a relaxation time, right? If it's very fast, I'm just going to deform the electric cloud. If it's a little bit slower, maybe I'm able to shake things around. If it's even slower, maybe I'm able to actually have that force in a specific direction that my ion can jump. So we have to be careful with this, that we have to think about how much time we're going to give for this thing to jump around. You can think about this, how much time you're going to give as a jump frequency concept. So this model specifically brought this idea of the jump frequency concept, which I think is very interesting. So as I said, you have now thinking about the jump frequency, the author wrote, here's the real part of conductivity, and he uses the diffusion coefficient. As I said, it's important for us, and again, now the jump frequency. So now you have to think how many times something will try to jump at a given time, and therefore you have to think about how much time you're giving for that ion to jump around. All right, I guess I have to move a little bit faster. The next model that I want to think about is a little bit larger. So now we're going to be thinking not so much on an ion jumping out of space from one defect to the next, but I'm going to be looking at the structure of the glass itself. So if I'm not mistaken, yeah, in 1985, Greaves, using XFs, thank you, using XFs, found evidence that the glasses are not as random as we thought, that there is actually some kind of preference within the glass structure. That idea, that concept, is known as the modified random network, meaning that it is random, but not really. We can see that very well here in this figure, in which you have these channels, these pathways, in which the ion can move around. So if you're familiar, would be a similar concept to maybe Nazi-cone structures, in which you have a preferred pathway, so you're looking for those channels. But that idea, as I said, the idea was from Greaves for the modified random network, and Ingram and collaborators developed an ionic conductivity model for that in 1988. And as I said, you have this, what they call connective tissue, in which they jump around and they have preferred pathways, they have some diverted pathways. So basically you're creating these preferential channels. Maybe it reminds you a little bit of the shell concept that Professor Thomas described a little bit. You just have preferred pathways within your glass. Of course, it's not a crystal, it's just more random glass, less random glass, more non-bridging, less non-bridging. All right. Then we can go a little bit closer to our days, and I promise I'll be done in a second so you guys can ask some questions. But we have this, what is called the migration concept, that is an anagram for, let me see if I can, whoop. the mismatch generation relaxation for the accommodation and transports of ions. I'm bringing this one because it's interesting in this, is that the authors look at the spectra of ionic conductivity. So you have the ionic conductivity as a function of frequency, and they're looking for the overlap. So they're, the authors propose that ionic conductivity fundamentally is one single mechanism that overlaps. It just changes on the composition itself, but fundamentally they should all behave the same if you divide then by the relaxation frequency. What is this one interesting is that the superposition depends on the successful ionic hops. So when something jumps, if it's successful or not. So it's going to be the jump frequency once again. The strictly localized ions and vibrational motion. So it starts looking a little bit on different concepts at the same time, right? So it has the successful ion hops and the vibration. So it's thinking once again on what or how fast something can move around, and also the strictly localized ion displacements. So the actual jump or the mobility. So it brings a little bit all those ideas together, somewhat. And the interesting thing then is that they also assume this to be all connected. They all have to be collective and cooperative. So you cannot have them individually. They all affect your ionic conductivity. A little bit more recently, way more recently, Mauro, Colin, myself, have this idea, presented this work in which there is a coupling between the ion hopping and the relaxation of the local network. So thinking about, if I have to make a loose analogy to the Polaron or discussion that we had earlier, but it's affected by the distortion of the network. And I think it's very nice. You can see here how you have the initial configuration, so the density of colors closer to red, more distorted the ion had to, or more out of the original place the ion is, and you can see that during the jump process, there's a really large distortion of the nearby network, and when it comes back, it has some distortion that both left behind from the jump and also on the new site. Little bit reminiscent of the Anderson-Stewart model, but what is interesting for this one is that it has a little bit of a more thermodynamic approach in which we are looking at the configurational entropy of these sites. So it's bringing a little bit more to the thermodynamic concept. And what is also interesting is that this one, we were able to get some good agreement with the literature only through molecular dynamic simulations. We are discussing all these models, and it's very nice to understand how the ionic conductivity takes place. But even nicer is to actually be able to design better glasses, right? So understanding science is important for us, but we also have to try to design better glasses for the different applications that already have been introduced. So I'm not going to spend too much time on that. All right, I think I'm just going to make a quick comment on a special also model or special interpretation of ionic conductivity. I know it's out of chronological order, but this not necessarily try to predict ionic conductivity. It's just an interesting relationship that was found, and there are some interpretations in the literature, but it's not extremely clear. So I'm talking about Haven and Verkerk work. I would say that this is very well known as Haven's ratio. It's even called HR. I feel bad for the second guy. But the idea is that you have this ratio between what we call the self-diffusion, which would be the diffusion without the presence of an external electric field, so just temperature jumps. And the diffusion because or due to an electric field. Why this ratio is interesting? If you go back to the ceramics, adding temperature should just change the number of ions that are jumping, but not necessarily their mobility, because you're not changing the energy landscape, right? As I said on that model from 1988, it all should be somewhat constant and flat. And this is true for most crystalline materials. That Haven ratio is actually equal to 1. So there's no difference in the diffusion. You're only concerned about the number of defects that are happening. Interestingly enough, for glasses, this Haven ratio is not 1. Otherwise, I wouldn't be talking about it, right? This Haven ratio actually varies. For low alkali concentrations, is usually around 0.7, and for higher concentrations, is usually between 0.2 and 0.3. And as I said, this diffusion is basically dependent on how fast your ion is moving. So here, I have the mean square displacement, r square, over time for simulated glass under an electric field on the x direction. And you can see that the ions on x are moving more, are going further away than the other ions on directions that you don't have an electric field. There are, as I said, a couple of interpretations of this results. One of them is that by applying an electric field, you're actually creating different pathways. So if you go back to Ingram's model, there are some ways that were blocked. So you can think that in when you have just thermal Brownian motion, you have some of those ways blocked, but by applying the electric field, you actually open the gates for some of those paths to move, to be accessible to your system. As I said, this is just an interpretation of the Haven ratio. I would say this is the most accepted one, but not necessarily a predictive for the ionic conductivity or activation energy. Nonetheless, very interesting. And of course, we can test some of those theories experimentally. A very popular way, I would say, at least in Lamav, is using the calculated mobility through Hall effect. If you're not familiar with it, Hall effect is how we actually measure mobility of many different systems. And fortunately, for glasses, it doesn't work very well. The signal is very weak and close to the noise, therefore making this very complicated. But there is one result published in the literature for silver phosphate glasses. The mobility can also be measured by discontinuity below and above Tg. Again, this was done by Marceau in a very nice article. We can measure the EMF of a battery. This was done also very nicely by myself. You have to be humble, you know. We can measure the blocking electrode capacitance that I still have to discuss more with Vinicius. You can try using molecular dynamics or other computational methods to understand this a little bit better. But it's not trivial to separate those two things, to separate the number of charge carriers and the mobility of your system. For the structural models, of course, we can use some structural characterization techniques. We can try to understand the structure of the glass a little bit better by the much beloved and known techniques. We can study Raman, we can study NMR, using calculations of free volume, which I don't know if I would necessarily classify as structure, but thanks. I got the thumbs up from the other structural guys. Great, I appreciate. We can try having some indirect measurements of other structural-related properties. So that would be, for example, mechanical properties. That would be the shear modulus. And again, we can use some computational methods. The previous example, I would say, is more molecular dynamics because things have to be moving. For this one, if we're looking at the structure, you can be still, so I'm suggesting Monte Carlo. From all this, just to wrap up this conversation of ours, if you look on the very fundamental basis, all those models being discussed since the 50s, there are people who are still pursuing their PhD and looking for this. This question fundamentally resumes into understanding that ionic conductivity is dependent on the number of charge carriers and the mobility of the charge carriers. The problem now is understanding what is a effective charge carrier, understanding what is the mobility. There are a lot of things that come behind this, and we can discuss more, but you can think about time dependency. Normally, we understand the charge carrier is an alkali, but it can be more things. The mobility, not necessarily, is just one thing. You can also think that we are not looking at the average behavior. You just need the more conductive things to move around. You don't need all the alkalis to be moving around. So this is a very simple but complicated question. It's not easy to answer. And just to summarize, as I said, we can divide either in weak electrolyte and strong electrolyte. Usually the structural models ignore or overlook the possibility of having a varying number of effective charge carriers, so they normally fall in what we call the strong electrolytes. Meanwhile, if you have the creation of these possible charge carriers, then you would have what we call the weak electrolyte. And here I just divide and classify them so you could just understand them a little bit better. I created this new category that would say time dependency, looking at the jump frequency as well, in which you have to understand how long or how much time it takes for your measurement to happen and to think about that part. And as I said, a big part of the problem is on separating charge carrier from the mobility and also understanding what is happening and to be able to understand what is happening on that time frame that you are. I'm going to just go to the questions part, and I'll be happy to answer all your questions. Thank you.
So thank you for this vivid and comprehensive talk. But anyway, I hope there are some questions.
Nice talk, Caio. The good thing about all this is that we still have a lot of work to do. So that's something that Ricardo also brought this, and we've been discussing this, about the necessity of putting all the glasses, I mean, let's say just the sodium and borate system. So different compositions, chemical decompositions, 02, 03, 0, and the necessity of putting them in the same page. What does that mean? Is that he showed the difference in conductivity with the relaxation. So I want to hear your thoughts about the necessity of erasing the thermal history of the glasses and in a such way that we can set the fictive temperature as the same as the glass transition temperature. So we are sure that the glass has relaxed and their fictive and TG are like the same and they are related to chemical composition. And from them, we start like performing any other type of experiments. I want to hear your thoughts about this.
Sure. So correct me if I'm wrong, just to see if I understand. You're trying to eliminate any possible variation from thermal history and just looking at what is actually happening within the glass, without. That's a good question. I would say that there are some things that are going to be eliminated. So I found a very small change in the ionic conductivity with the thermal history. Ricardo found a little bit bigger. But still, we're talking about 1 order of magnitude, right? And if you think about compositional dependency, we can vary like 6 to 7. I think what is challenging is that I do not believe that neither the mobility, the number of charge carriers is a little bit easier to understand. That's changing by 7 orders of magnitude, right? But that proportionality to deposit everything in one of them seems a little dramatic. I think from what I understand from your own results, you didn't put everything in one. You put a little bit on the number of charge carriers and more on the mobility, right? So I think there's some of that. I don't know if the dependency would be then eliminated. So for example, your small dependency on the number of charge carriers, if you relax, you're going to have a fixed number, and that's not going to change, and then you're just fluctuating that. Or if you're affecting the mobility, again, just creating a path. This is something that I was discussing with other friends of mine. I think there's also, there are two things that we have to think about, right? There's a very large commercial interest in this kind of glass. So to be able to predict what the ionic conductivity of a certain composition with a certain thermal history is going to be is very powerful, right? If I could predict that, I would make a solid state high ionic electrolyte, and I would be selling that to battery companies, and maybe I would be making some cash, and I wouldn't be around. I would be on the beach. But at the same time, you want to understand the science behind it, right? You understand, you're curious about it. But I think, as it was said many times, we're talking about models. So we're just trying to understand and replicate reality. There are no actual paths. Atoms are not spheres. There's no sticks. So I think it's just trying to understand, back to your question, a little bit on, by relaxing the glass and going to the fictive temperature, am I going to just reach an equilibrium of dissociation that we haven't reached yet, right? So that dissociation equilibrium from Suke's proposal, is that actual the dissociation? Are we going to reach an equilibrium? Or am I thinking about, is the structure going to be fixated on the paths, and that energy landscape is going to be a little bit more smooth? So I think those are two ways of interpreting. I'm not giving an answer because I don't know, but I'm giving you thoughts.
More questions to think about.
Yeah, of course. It's the mysterious master that doesn't give the answer, just more questions.
Any other question?
Let the student ask first. Good.
So you showed many models for ionic conductivity in glasses, and I'm thinking if these models are maybe somehow complementary, or is it some evolution of one model to interpret even more, to get more agreements, or maybe it is some other situation?
In my opinion, they are not completely independent, but I think sometimes they're also not complementary. I think it's like an evolutionary tree. There were some branches that branched out. And I think that's more or less where the weak and strong electrolyte ideas came from. And is there an energy associated with creating this charge carrier, or this is not necessary and just goes? Yeah, I would say so, yeah. That's why I put them in chronological order too. Marcio had one question. Someone else had a question? I don't know. I think it's you, Marcio.
Hi, Caio. Nice talk.
Thank you.
Just a simple question, right? In your thesis, you proved that for the silver compound, silver phosphate, you proved that conductivity is proportional to activity, right?
Yeah.
And in that graph, it's clearly shown that the mobility is just the tangent.
Yeah.
It's constant.
Yeah.
But there are other models, you know, you just presented, that where the mobility is not almost constant. So, what do you think about that?
You're telling me to pick one, is that it? I actually, when I'm recruiting students, I joke with them that this is my holy grail. So maybe this is a reference that's a little bit old for you guys, but Indiana Jones and the Holy Grail, at the end, he goes into a room that is filled with different cups, and the challenge is that he has to pick the Holy Grail. On the spirit of the model, I think it really depends on what you're trying to interpret, what physical meaning you're trying to get, and how well it describes reality. So I would say that for this system, the weak electrolyte describes it really well. Is it necessarily true that is the dissociation or the activation energy. I don't know, but it describes well, right? And then can I extend this to other different glasses? I think what is dangerous is the concept of glass is very broad. And to say that every glass follow a single model is a little bit complicated. Right now, I'm falling into the idea that we have strong electrolyte glasses and weak electrolyte glasses, right? So some of them, I think all of them are going to have a dissociation energy associated with the formation of charge carriers, but I don't think all of them are going to be weak or all of them are going to be strong. I think it's going to depend a lot on the former, on the alkali, and maybe even on the thermal history, for example. So yeah, that's more or less where I'm falling right now. Do you want to complement that, Anna?
The very last question, please.
Sorry, I just want to push you on that point a little
Okay.
bit more. Because that's a very political answer you gave us.
That is a very political answer, yes.
Everyone-
My PhD advisor is here. so-
Everyone's right. Right is what you just said. Everyone's right to some degree.
No,
but,
I
like-
think everyone is wrong to a certain degree.
Oh, but if you're saying that there's two different mechanisms for two different types of glasses, I was wondering if you had a little bit more detail about what decides if a glass is one thing or another, and if everyone's a little bit wrong, where do you see the future of this research going?
Okay, so I'm going to answer your question first. Colin is pushing me to pick a side, and I'll pick a side. I think the mobility is less important, and I think the number of effective charge carriers is more. What pushed me into this direction is the high change with composition that you see. So I don't think if I made that clear, but I mean, I know I didn't make that clear because I was moving a little bit faster. But here you see, maybe you don't. So here you see that on the left graph, the ionic conductivity is changing by 3 orders of magnitude, although I'm changing the composition from 0.2 to 0.5. So I do believe that to change this by 1,000, to change that by 1,000 is not enough to just change the mobility, or it does not make sense that mobility would be changing. The ions would be moving faster 1,000 times, for example. So I do believe is the number of effective charge carriers. The research where I think this is going is now understanding how can we make a glass with more effective charge carriers. I think not only glasses, but also thinking about glass ceramics even, but it's trying to tune into that, and of course trying to progress into making glass that would be more efficient for solid-state batteries, sensors, so on and so forth. Predictability, I think that's the key. It's not just the model, but how can we predict a good glass?
Nice talk, Professor Kao. So just the basic of the ion conduction motion, which is the Anderson-Stewart model. So I want to talk about the assumptions which the model takes in order to come up with a formula. So I think the Anderson-Stewart model, it is basically taking an assumption that it is a two-body interaction. So maybe it's between two ions. So yes.
So you're assuming, you're asking me if it's a two-body interaction, or?
Yes. So I wanted to ask, like, how can we account for the interaction between all the ions in the system? Like recently, there has been a model which is CMAS model, that is Christensen-Martin-Anderson-Stewart model, which is a development of this model, and it has a constant called Madelung constant, which I think accounts for the interaction between all the ions in the system. So can you tell us something about the...
Madelung constant is actually there. Anderson and Stewart have the Madelung constant.
Yeah?
They do.
Oh, okay.
Yeah, so this term already existed. In their model, they just, I tried to move fast because I didn't want to spend too much time on it. But the Madelung constant is here. And on their work, they assume it to be constant, or it doesn't affect the ionic conductivity itself. I know about the model. I have to read it a little bit more.
Yeah.
I don't know if they're taking into account interchangeable Mendelian constant or an evolutive Mendelian constant. But in this case, they do have the Mendelian constant. Is actually one of their fitting parameters in their
Right.
equation.
Yeah.
But in the end, they assume that it's a constant.
Okay, so they are, I think, assuming that the Mendelian constant is equal to 1 for maybe. And they are not accounting
I don't
for
remember. I don't think it's 1. I think it's like a fitting parameter.
It's a fitting parameter, but here, which one is the Mendelian constant? Is it
It's within
Beta?
it's within
beta, I guess?
yeah.
Beta.
Yeah.
Okay.
It's within the binding energy. So what they say, if I'm not mistaken, I don't want to be totally wrong here. So basically, we should read the paper again. But if I'm not mistaken, they assume that the fraction of beta and gamma given to a constant value.
Okay, okay. Thank you.
Okay, thank you. So that was a very nice discussion, but I think we should move to the next
I'll talk later.
lecture.
Thank you.
You can talk later. And now let's welcome Professor Ana Rodriguez from IFSC, so you know her perfectly well. And the floor is yours.
So let me see if I can manage this. Yes, I think so. So now you know everything about electronic conductivity in glass, about ionic conductivity in glass. So let's see how can we measure, especially ionic conductivity in glass. So is it easy to measure? Is it not easy to measure? Why I should talk about measuring ionic conductivity of glass? There is no title of my presentation, sorry. As a background, this is the wrong presentation, sorry. This is the wrong presentation. So that's it. So I will talk about something about impedance spectroscopy or how to measure electrical conductivity of glass. So first of all, I'm sure anyone who had dealt with electrical properties here have dealt also with impedance spectroscopy. So the first question, simple question, what is the electrical resistance? So the answer is not, I would say it's the obstruction of the current or electrons or charge to flow. Not very important definition. So it's the resistance of the electrons to flow. And then what is the impedance? So I will ask you to wait some minutes to see some more slides, and we will ask this answer. So the first question is, what is the impedance? When my students come to me, they have some difficulty to answer this question. So then let's look. What is the obstruction of the electrical current or electrons flow? So when you have a sample, can be a metal, a ceramic, a semiconductor, if you apply an electrical voltage here, an electron potential here, you will measure an electrical current. And the resistance of your sample, it's the ratio between V and I. It's Ohm's law, so very simple. The electrical current increases while you increase the electrical potential, and the ratio, the slope of this straight line would be the resistance. But now you will, in impedance, you will apply an alternating current, so it is a sinusoidal signal which changes, V changes with time, V equal V0 omega sinus omega t with time, and you will read a sinusoidal also current with E equal E0 sinus of omega time with V, and the current lags the voltage by an angle, by a certain angle. So in impedance, you will apply an alternating current, and you will read, the result will be an alternating signal which varies with frequency, with variable frequency also. You will also vary the frequency. And the impedance will be this ratio, V, which is changing with time, over the current, which is also changing with time. So before going further, I will already show you that any ceramic sample, semiconductor also, but not metals, for an obvious reason, can be represented by a parallel RC equivalent circuit. This is the most simple equivalent circuit for a ceramic. Why not metals? Why I cannot represent metals by this equivalent circuit? Because metals has no this capacitance, this capacitive contribution. All ceramics will have a capacitive contribution. Okay? So then I will just remind you what is a parallel plate capacitor. You have here an ideal parallel plate capacitor. When this capacitor here is discharged, when you apply a voltage, the current is maximum. Oh, this is tricky. The current is maximum here. Why the current is maximum? Because all charge wants to move very fast because of you applied a difference of potential. So all charge will move very fast, and then they will start moving, having less current, and in the initial time, t equals 0, time equals 0, you have 0 voltage, and it will be maximum voltage when current is 0. So when the capacitor attained this stage here, so with maximum charge distributed between the two plates, you will have a maximum voltage, and you will have 0 current. Oh, God. Okay? And this will continue. So this is in, how do I say, in, I am here in, sorry, I'm missing a name. In a moment, I will tell you. Okay, so in this case, we say that the voltage leads the current by 19 degrees, or the current lags the voltage by 90 degrees. So this is very important. Why I am talking about a capacitor? Just because our equivalent circuit will have a capacitor and a resistance in parallel. So then you know that this phase angle, which is this phase angle, it will be exactly the same of this one. So this is the phase angle. This is the origin of this phase angle. So Then here, again, I am applying a sinusoidal voltage, which is changing with time, and I read a sinusoidal signal, which is changing with time, and I have a time shift here, and my impedance will be V over I. And what's the problem? What's the problem? The problem is that V is changing with time, E is changing with time. Sometimes the current is 0. So when the current is 0, what do I do with this ratio? I cannot calculate it. Okay? So that's a little bit more problematic than applying Ohm's law, U equal R equal U over I. So then I can say the impedance is a resistance measured by an alternating current and variable frequency. That's it. For me, that's it. Students must remind that the impedance has an unit, ohms, is exactly the same unit as the resistance. So it's a resistance, but it is measured by alternating current. So, and how do we calculate this ratio? That's the problem now. How can I calculate this problem? I cannot calculate by a simple ratio like this. That's why I will apply complex number. So it is called complex impedance because I will apply here some mathematical trick to find a complex number because it cannot be solved like this. That's why, so the impedance is a physical characteristic. It's a very physical characteristic, but to represent it, I must have a complex number. So I will represent this property using complex number. So that's it. Impedance Z will be represented as a complex number to solve this problem. What is a complex number? I believe all of you remember what are complex numbers. Complex number may be represented by a series in more than one part. So the easiest one is this Archan-Gauss plane. So I have all natural number may be a complex number if I, the imaginary number here, I, is 0. So if I is 0, Z would be equal to A. I can represent this imaginary number by this is our phase angle. This is exactly the same phase angle where I talked about. So we will have the modulus of the imaginary number and an angle. So the real part will be Z cosinus phi, and the imaginary part will be I cosinus phi, I rho cosinus phi. I think this is not new, but it's nice to recall it. So the algebraic form is this one. This is the conjugated of the complex number. So the polar form is Z equal to the modulus, rho cosinus phi plus I sinus phi, and this is the conjugated. So then we have here the Euler formula. Euler was a Russian mathematician, very well known. He proposed this formula here. E is elevated to minus I pi equal cosinus pi minus I sinus theta. This seems complicated, I don't think so, but when theta equal to pi, we can say E to I pi plus 1, because cosinus theta equal 1, I sinus theta equal 0, we can write something like that, okay? This is really a super formula. Why? It is really very complicated to imagine. You can imagine here. So we can imagine what is E, it's the Neperian number. what is E to IP. This is really complicated. We cannot imagine what means E elevated to an imaginary number and even to a non-rational number like P. But EIP plus 1 equals 0 seems almost a miracle, okay? But this was proposed by Euler. Why is it important for us? We will apply to solve this. This is equal V0 sinus omega t, the current I0 sinus omega t plus phi. We will apply a Fourier transform here. That's not very important here for us. And then we will arrive to the Euler's formula. And the Euler's formula, we can work with it. The Euler's formula, we will have this Euler's formula, and we will say simply it is cosinus theta plus I sinus theta. That's why this Euler formula is important to us. So we will have, finally, after some complicated mathematical transformation here, we will transform this ratio in something like this, okay? That's why it is a complex number. So, okay, that's all. We have Z cosinus phi. This is our impedance. Note that V and I vary with time, but Z does not vary with time, but with the phase shift angle, okay? Then, this is our expression. We will use omega, frequency omega equal to PF. We will have variable frequency. This will be fundamental in impedance spectroscopy. And Z will be the impedance function, and its value at a given frequency is the impedance of the material at a given frequency. Note that the unit of impedance is the same unit as a resistance. That's why I say the impedance is a resistance, but measured in alternative current, and we use variable frequency. This is also very important because we will separate different phenomena with different time constants. We can separate by impedance spectroscopy. Remember that this variable frequency, this name, spectroscopy, reminds us about variable frequency, okay? Spectroscopy is the study of the interaction of light, of waves, interaction with light as a function of frequency. Okay, then another important question. Then you know now that you will measure impedance, you will measure simply the resistance of the material, but applying a variable frequency with an alternating current or potential, and you will read variable frequency. But why use alternating current? Why not simply applying Ohm's law? Why I cannot take a potentiostat, I apply the potential, I read a current, and the resistance is the relation between my potential and current? Shweta, any idea? Any idea? Why we should bother with all of this? Dealing with ionic material, okay, I have here an ionic conductor. I will apply a potential. My wires here are electronic conductor. I believe my ionic conductor is not electronic conductor, or the electronic conductivity of my sample is negligible, so he is mostly electronic conductor. Then, if I measure by Ohm's law, applying Ohm's law here, V equal Ri, I will measure a potential here. I will measure several kinds of, I will measure resistance of contact here, because the ions cannot go to the metallic wires, and the electrons from the metallic wires cannot go to my ionic conductor. So I will have an an extra potential here, an overall an anodic and cathodic overpotential or overpotential, and that's why. So I will measure R, I will measure this resistance R of the ionic conductor, but I will also measure all of this. So I cannot separate exactly the resistance of my sample from all those resistance, those extra resistance which appears because of the contact between an ionic conductor and an electronic conductor, which is my metallic wire from my apparatus. Okay, the advantage of applying impedance spectroscopy. It studies the transport phenomena in semiconductor and ionic conductors. It separates phenomena with different time constants. The time constant is the product R, resistance and capacitance. If you take the units, the SI units of resistance and capacitance, you will see that the product of both is second to -1. It's second, sorry. That's why we call it a time constant. In ceramic, impedance spectroscopy separate contribution from grand boundary, and electrode phenomena. I will talk about what is this electrode phenomenon. Also, it measures the material resistance by eliminating this electrode phenomena, which would not be eliminated if I apply an Ohm's law or a direct current. Okay, impedance I use most of the Z-plot, the impedance plot, but it's important to know, to remind that there is more formalism of impedance, so the admittance is Z over -1, is the inverse of Z. The dielectric constant is the inverse of this modulus. This modulus is this mi over Z. So, and which is the best formalism I can use? To know the resistance of the sample, we can use Z. This is the best formalism. But some authors, there are lots of study which applies other formalism to see phenomena that they cannot see in impedance. Sometimes we have, for instance, 2 peaks in modulus, but we do not have 2 peaks in impedance. So the idea is to combine several formalisms, but just to calculate the resistance of a sample, glassy sample, impedance usually is enough. So, and the impedance is mostly represented by the Nyquist diagram or the Nyquist plot. What is the Nyquist plot? You take the real part of the impedance. I showed you that is a complex number. So you will take the real part of the impedance number. You will plot on the x-axis. You will take the imaginary part and you plot on the u-axis. And this is the Nyquist plot, like this. It's a semicircle. So I read already that Nyquist was a researcher from Bell, I think in the United States, and that Nyquist did not really work with this diagram. The condition with Bell worked, it's not really the same, but this is now in the common sense, or we always call Nyquist diagram. Why I say real part in the x-axis and imaginary part in the u-axis? Because the u-axis is not a function of x-axis. So sometimes the students, when they are beginning, they say, oh, imaginary part is a function of real part. No, there is no mathematical function which links the imaginary part to the real part. So, and remember, each point, it's a different frequency. That's why also there is no link between both diagrams. You can see that if here I wrote the frequencies. If I do not write the frequencies, there is no information about the frequencies here. If I do not write it, so the Nyquist diagram lacks on the information of frequencies. Observe that this is the modulus of the impedance, and this is our phase angle, okay? And in this case, the frequency increases from right to the left. So each point represents the impedance at a given frequency. The impedance function varies with the frequency. You see that the modulus of the impedance is changing with frequency, okay? It increases when I decrease the frequency. This is 10 to 3, this is 10 to 2, this is 10 to 4. When I decrease the frequency, I increase the impedance, the modulus. The modulus, I mean the modulus in the term of a complex number. So the equivalent circuit that best represents the experimental points is a parallel RC circuit, resistance capacitance. Best means this is the simplest circuit. I will talk about the capacitance a little bit later. So then those are the elementary circuit in the complex impedance plane. We can take, if I take a resistance, a pure resistance, and I will calculate or I will represent Z, the impedance, my impedance does not vary with the frequency. So here I will vary, I will apply an alternating current, an alternating potential, electrical potential with, and I will add an alternating current with variable frequency. If I take a pure resistance, this impedance will not vary with the frequency, okay? But if I take a pure capacitance, the impedance will vary with the frequency, like this, 1 over I omega C. So I added R here, I added a resistance here in series just to show you the capacitance. If I do not have this R, the straight line will coincide with the Z-axis and we will not see, we could not see. So the parallel, a series of RC circuit, we will see a semicircle. I can demonstrate you mathematically that it is a semicircle, but we will not do this now. If I take a semicircle followed by a capacitance, I will have, if I take a RC circuit followed by a capacitance, I will have a semicircle and a straight line. If I have an ideal capacitance, I will have a straight line here at low frequencies. Remember that high frequencies are on the left. So the Nyquist diagram, let's talk a little bit about it more. So the resistance of the sample is read in the intercept of the real axis, x, in low frequencies, okay? Remember that I have high frequencies are like this, frequencies are increasing like this, frequencies are decreasing like this, and I will read my resistance here in the intercept at low frequency. So here it is an ideal equivalent circuit. Each point is a different frequency. Impedance increases with decreasing frequency. The phase angle phi decreases with decreasing frequency. And I read my sample resistance here. This is an example of a glass which has no grains, no grain boundaries. At the apex of the semicircle, where the imaginary part is maximum here, okay, we can have the relaxation frequency. The relaxation frequency is the only one which satisfies this relation, omega RC equal to 1. If I have the relaxation frequency, if I have the resistance here, I can calculate the capacitance. So what most of our software, like the View, our common software does, they by least square fitting methods, they first estimate the resistance, they know the frequency in the apex here. It's not only by eyes, but there are a method to know this, and then they calculate the capacitance. This is what most of software does. So, omega, which is the importance of this relaxation frequency. If I have 3 variables, the frequency R and C, I can calculate the third one. So if I know resistance and frequency, I can calculate the capacitance, for instance. So the capacitance is not directly read from the Nyquist diagram. The resistance may be directly read here, but not the capacitance. To infer the capacitance value, I must know the frequency. So the resistance R is read at the intersection of the semicircle, okay? Okay, there is no direct reading of capacitance. It is calculated from the resistance and relaxation frequency. So, what is the importance of this relaxation frequency? The relaxation frequency is independent of the geometrical parameter, while the resistance, I'm talking about resistance, not resistivity, while the resistance depends on the geometrical parameter, the thickness and area of my sample. The capacitance also depends on the thickness and area of the sample. The relaxation frequency depends only on the conductivity and the relative permittivity of my sample. So the relative permittivity is independent of the geometrical capacitance, the geometrical parameter, but not the capacitance. So F is a characteristic of the material which depends on R on C. This is very useful, for example, when I have grain and grain boundaries, when I have a glass and a crystal inside this glass, because I cannot know the geometric factor of all this little crystal, so the relaxation frequency will be important to help us calculating the conductivity of a second phase, for instance. And 1 of F0 by relaxation frequency is equal to the time constant of the material. So the impedance spectroscopy is independent of geometrical parameter. The impedance, this is just playing games. If someone here has already tried to do impedance spectroscopy, sometimes they say, oh, I do not have a complete semicircle. Why you do not have a complete semicircle? Because you do not have enough frequencies. So if you do not have a complete semicircle here, you do not have enough high frequencies. Maybe you must go to gigahertz because most of equipment, of common equipments, go to 10 megahertz, 13 megahertz. If you do not have, like here, oh, I do not have a complete semicircle. What's wrong with my sample? Nothing wrong with your sample. It is a lack of frequency here in the low frequency region. So you can either change equipment, you can either increase temperature, and you will have your complete semicircle. So to have a complete semicircle, you must have for all materials, about 3 orders of magnitude. You may vary the frequencies from 10 to 6 to 10 to minus 3 to 10 to 3. Normally, if you have 3 orders of magnitude in frequency, you will have a complete semicircle, but those frequency, of course, depends on the time constant of the material or on the RC product of your material, okay? So and if you do not have a complete semicircle, you can also play with temperature. Increase or decrease in temperature, you will see a complete semicircle. So, which is the influence of the geometrical parameter? Does the geometrical parameter influence the how does it influence my Nyquist diagram? So I told you we read the resistance of the sample, not the resistivity. So this is a very old example. They just played games with the geometrical parameter. For instance, here they kept the diameter, and they changed the thickness. And you see, if I have a low thickness, I will have a low resistance. I will have a low semicircle. But the relaxation frequency keeps constant. Okay? All the frequencies keep constant. The distribution in fractions will be the same if I only vary the geometrical parameter of the sample. What will change here, frequency, resistance, what will change here, it will be the capacitance, because the capacitance varies with the geometrical is different for each geometrical parameter. The dielectric constant is constant, but the capacitance will change with the geometrical parameter, and but the frequency here will remain constant. The resistivity, which includes the geometrical parameter, of course, will not change. So this is the influence of temperature. So I have my sample, I have the same material, and I'm varying the temperature, and I see, oh, okay, nice. My resistance here, my semicircle is decreasing, my resistance here is decreasing, that's normal, and you cannot see, but when I increase the temperature, all frequencies go from left to the right. So you cannot see here, but 20 was here, 20, this is 75, then 75 will be here, then 75 will be here. This is very old examples, but it's still valid. This was a glass from Jean-Louis Souquet, still an example, from Denis Raven thèse. Okay, this is an example with glass, okay? This is a simple glass, a borosilicate glass. We see when we increase the temperature, the resistance decreases. That's normal. Here I was measuring a lithium niobate ceramic sample. Also, temperature increase, resistance decrease. And please look at this spike or this straight line. This is not really straight line at low frequencies. This will be the electrode phenomena, what we call electrode phenomena. I will talk about in some minutes. Okay, as the temperature increases, the frequency shift to the right. That's what we have seen. Why? Then why? Why the frequencies shift to the right? Because, as I said, as we can see, the resistance decreases, the capacitance does not change a lot with the temperature, should not change. So if resistance decreases, the RC product, as we said, 2 omega RC equal 1. If resistance decreases, capacitance is constant, so the relaxation frequency must increase. That's what we see here. So that's what we see here. 100 kilohertz at low temperature was here. Then it shifted to, we shifted. So all the frequency will turn here. That's why we can say that the relaxation frequency increases with temperature. We can also do an Arrhenius plot of the relaxation frequency. It will be the same activation energy as the conductivity, or almost the same activation energy. Okay, this is also an old graph, but I like it very much. This was old times when the equipment had no big frequency range. So look what is happening. This is a zirconia solid electrolyte, as a classical zirconia solid electrolyte to be applied in fuel cell as solid as oxygen conductor. So we have here, at this temperature, grain and grain boundary. Then we increase the temperature. Here the semicircle of the grain boundary is not complete. We will increase from 570 to 620. We have both semicircle completed, because frequencies are shifting to the right. Then we still increase the temperature, and you can see that here, this first semicircle, the left semicircle, the high frequency semicircle is starting to disappear, okay? Then still higher temperature, this semicircle is almost completely disappeared, and I have a third semicircle on the low frequency size. This is due to the electrode phenomena, okay? So the range of frequency, of course, are the same. They started here, I don't know, 10 to 3, and they finished to 10 to 1. So, but as the temperature increases, all frequencies will shift from the left to the right. So, this is, I measured here some lithium niobate polycrystal. This was a nice sample. So, this is log conductivity and log relaxation frequency. And I see that the activation energy is very similar. It's not identical. Maybe it is on the experimental error. Maybe there is a reason for that, what I will tell you now. It is because the semicircle is not, it's not, the center of the semicircle is not on the x-axis. Though this was a very interesting paper, so I measured a lithium niobate single crystal. When I measured it, so I had someone gave me a single crystal lithium niobate, and I measured the conductivity in two axes, z-axis, x-axis, and I have no change in the conductivity. But when I plot the relaxation frequency, I see a clear change when I change from x to z-axis. It means that the conductivity does not change following the axis of this single crystal, but probably the dielectric constant, the relaxation process are different in the x-axis or u-axis. Okay, but everything was very nice, but those who worked already with impedance spectroscopy knows that the center of the semicircle, it's not on the x-axis. The center of the semicircle, it's always, there is always an angle between the center of the semicircle here and the x-axis. So why this? Because this capacitance, which I wrote here, it's not really an ideal capacitance. It's what we call a CPA, constant phase element, with the phase element different from 90 degrees. Because the ideal capacitor is also a constant phase element, but with an angle with the x-axis with 90 degrees. So we have here a decentralization angle. In glasses, it's very easy to explain. I have a glass here, so a glass is not an homogeneous material. I have a crystal here, so it's like I would have several little glasses, and several little glass, and each one of these little glass will have a different relaxation frequency, and that is the cause of this phase angle. If I measure a single crystal, theoretically, I would not have a decentralization angle, theoretically, because we find a much smaller than in glass. In glass, the characteristic decentralization angle, it's around 10 degrees. In a single crystal, it will be 1, 2, because even in single crystal, we will have defects, okay? So, for an ideal capacitor, I have those expressions, which I have already shown for the equivalent RC circuit. So I have here the imaginary number, I. Sorry, I must correct it for I to. Okay, so for the RC ideal, I can have this expression. But if I have a CPA, I will introduce here my phase angle. So this is 1 minus the phase angle, this alpha. And because of this, the expression to for my software are much more complicated. So it would be very nice if I do not have this phase angle, my real part of my impedance is this expression. It depends on the capacitance, on the resistance, and the imaginary part is like this. But if I have this alpha angle, so look, the expressions are very much complicated. But you don't need to care about, because nowadays we have software, we have commercial software, they do this job for us. But it is important to know what is behind the software. So we are scientifics. It's very important to know how the software, what is recalculated. So don't believe in the results of, or believe it, but you must understand what is behind, okay? I think this is very important. This is the effect of this phase angle, okay? If alpha is equal to 1, I have an ideal semicircle. If I increase alpha to 0.9, 0.3, 0.7, 0.5, so I will have what I call a depressed semicircle, okay? This is the effect of this phase angle, which is found in all materials. I worked already with one material in which I found this phase angle really a polycrystalline material. It was sodium niobate, which I found a very, very little phase decentralization angle. So, let's talk about now this part here. So, I don't know if someone here is working with ceramics or maybe glass ceramics. In glass ceramics, we can find a semicircle due to grand and to grand boundary, okay? But this is not a glass, this is a simple glass, but I will find this phenomenon of electrode, this will be always there. This is the signature of an ionic conductivity. This is the signature of an ionic glass, okay? And just note that the straight line is not perpendicular to the x-axis. So there is an angle here, okay? If this angle is 45 degrees, we have what we call a Warburg diffusion. When I showed you before that if an ideal capacitance arises, so we will have a straight line here with an angle of 90 degrees. This is due to a capacitance, to the electrode capacitance. I'm finishing. So this is due to what we call electrode capacitance or electrode polarization. Why is it? It reminds that if I'm working with lithium or sodium, I will have lithium coming from my electrolyte, and I will have electrons coming from my metallic electrode. And in the interface, I will have a capacitance. Plus here, minus here, this is a capacitance. But it's not an ideal capacitance. Why is not an ideal capacitance is a big discussion. They say maybe some lithium ions can diffuse in the gold electrode. I work with gold. Maybe there are some people talks about a fractal interface. Maybe there are some voids in this capacitor. So anyway, it's not an ideal capacitance, and to not, most people talks about lack of ideality. So as longer you are far from the ideal capacitance, you will have lower angle here in the electrode polarization. This is another example. This is just a glass, okay? Just to show you this electrode polarization. This one is a very, I say a very beautiful one, because this angle is very near 45 degrees, and this very near the Warburg diffusion. Just an example. So remember that high frequencies are here, and here we have low frequencies, and the impedance spectroscopy can look that it can separate the bulk properties from the electrode properties. Coming back, if I apply Ohm's law, or if I apply direct current, I will not be able to separate those two phenomena, because each phenomena here occurs, responds to different frequencies. That's why I can separate by impedance spectroscopy. If I apply a direct current, I have no variable frequency, I cannot separate it, okay? The same happens with ceramics when I separate grain and grain boundaries, because grain and grain boundaries have different RC products, so different time constant. Okay, and what happened with electronic conductivity then? With electronic conductivity, I do not have this electrode spike due to electrode polarization, due to ionic conduction. And why I do not have this spike? Because electrons can move to the wire. So I will not have then electrons piled up in the interface. Okay? So electrons can move, and I have an electronic conductor. This is a strong indication that I have electronic conduction in my glass. This was a bismuth iron phosphate glass, which is purely electronic. So, application of impedance spectroscopy, ceramics can separate grain and grain boundary. We can study electrode reaction. In electrochemical cell, I can study electrode reaction, diffusion, corrosion, so on. So, in glass, this is good candidates for solid electrolyte. Why? Because they have cationic transport number very close to 1. They have good electrochemical oxide glass or redox stability. They do not degrade quickly over time. However, oxide glass, I know some students here have already noticed it, oxide glass still have a low ionic conductivity, oxide lithium glass. But that's why we changed to glass ceramic. So, thank you very much for your attention. And if you have questions, maybe here, maybe the coffee break, I will be happy to answer. No? No time?
Thank you, Anna. Unfortunately, there is no time now for questions because this is the last opportunity for the poster session. Well, maybe one or two questions. Okay. Some people are really anxious to.
Yes.
So I wanted to ask about these electrode effects. At one slide you showed the temperature dependence of frequency, this characteristic frequency, and there was a Nyquist plot where we saw that the line connected to electrode effects bends, and it bends towards the x-axis. At one of last slides, you showed that it bends in the opposite direction. So my question is, how can you explain these electrode effects, and what is the difference between them?
This.
Yeah, but there was also another Nyquist plot where it bended in the opposite direction. So how could you explain the difference?
Another Nyquist. If it bends in the direction of low frequencies, it may be an indicative of an electrochemical reaction. So this electrode reaction here in zirconia, this electrode reaction is an reversible reaction. This is very well known in zirconia. Oxygen 2 plus electron equal to oxygen 2 minus. So this is very well known for zirconia. So, and the resistance is the resistance of transfer charge, electron transfer, and the capacitance is the capacitance of the double layer. This in zirconia is very well known and accepted. So if I have an ionic conductor like a glass lithium conductor, sodium conductor, it may be indicative that I will have, at very low frequencies, some kind of electrochemical reaction. But we should avoid it. This direction, electrochemical reaction. This direction, I have seen that the limit would be a straight line. So there is no this direction. The limit will be a straight line here. In low frequency, it will reach an ideal capacitor. I don't know. I must look. I have the figure in my mind that the limit it's a straight line, but I don't know exactly why.
Any last short question?
I hope it's fast. You said that we could use this technique to study corrosion. How would be that?
People who study corrosion, we normally study it in liquid. So they apply, they drop a metal in some liquid, and they do electrochemical impedance between some two electrodes, and they will see the increasing of some layer, some corroded layer in the metal, because of the resistance will be changing and so on. But there are some other parameters also. They can have access to the current corrosion, what they call. But it's almost they drop a metal in some liquid and okay.
Okay, so let's thanks again our two professors this session.
Thank you very much, Mr. Chairman and Kyle and Anna for the interesting session. Just some final announcements. We at 4:30 we have two lectures from Corning, USA, online. It will be top-level people at Corning, like the research director, Tim Gross, and then Paulo Dianese, who's a Brazilian guy who works for Corning on optical fibers. Regarding the posters, if after the poster session, in the end of the session, you can take your posters. If you do not want to take back your posters, you can leave them here. We will take them to LAMAV and hang them out at LAMAV for a month or two, so our students can take a look, and the professors can take a look in your research work, okay? So I think that would be cool to leave your posters here for some time, but feel free, it's up to you. I heard from Laurie that some people had some issues regarding your per diems, your money. So this is your last opportunity to talk to her. Make sure you get the proper amount of money to cover your hotel and your meals, and she'll give some extra cash if you need during the dinner tonight, right? On the other hand, if you got too much money, we are here to get some back, no problem. O posters. Isso eu tinha falado já, mas yeah. Another thing is regarding the bus to the dinner. The bus should be ready at 6:30 to take you out to dinner. And then tomorrow morning, we have a visit to Eduardo's lab and also to Andrea's lab. Yeah? To the other campus of USP. It's a little bit far from here. So we have to leave early because I know it's to move a large group of people. Like we had this experiment done at LAMAV, it's a slow process. This kind of the slowest moving species dictates, you know, the speed of the group. So let's agree on a adequate time. Say 8:15, leaving tomorrow. Good? 8:15? It's a little bit early for the last day, I know, but then you have to go back to São Paulo. And then 8:15 is 2 labs to visit, you know, a lot of people. I think you should be back at the latest, really latest, at 11 or so to the hotel so you can pack, you know, settle your bills and, you know. So, Eduardo, please make sure that 10:30, leaving at 10:30 from the USP to be at around 11 here. They have some time to refresh, etc. And by 12 maximum you leave to São Paulo. Okay? Ana, you wanted to say that there are still some posters of the International Year of Glass. If you want some posters, they're here. The students, the officially registered students for credits should sign, if they're here, should sign this list here. And any questions regarding the logistics, regarding anything? This is the last opportunity.
So this was made by Japanese Ministry of Education. So in honor of the International Year of Glass, they have translated, it's all functions of glass. So how glass is in our daily life. It's a very nice poster. We have the translation in Portuguese also, but this is the English translation. So it's a summary of
Okay. If there are no further questions, we have a coffee break now. And please be back by 4:25. 4:25. I know this is an impossible task, but I keep asking you, you know. Because it's 4:30. 4:30 the class starts. So 25.